Hello, my name's Will Greenwood. I manage higher education content at MathWorks, and I'm very excited to be joined by Paul Karam, Director of R&D at Quanser, to discuss the topic of virtual labs and how they can be integrated in engineering education to help build impactful hybrid lab experiences and what we can do going forward. So I'm from MathWorks, and you may know us as the makers of MATLAB and Simulink. We're very grateful to have many partners at ASEE, and we're fortunate to partner with over 100,000 businesses ranging from Fortune 500 companies to startups in over 6,500 universities. And as a result of this, we're able to see the challenges both universities and businesses are grappling with and the changes that they're undergoing. And many of these industries that we work with have been fundamentally changing over the past several years based on their use of data, modeling, and incorporation of other technology. And this is a concept that we're calling digital transformation. An example of digital transformation that most are probably familiar with is the development of advanced driver assistance systems and more generally electrification in the automotive industry. And many of these features use cameras and other sensors to assist the driver by automatically braking or accelerating to maintain distance from other vehicles and mitigate collisions. They're now becoming standard on many new cars in the automotive industry. And these features have fundamentally changed how vehicles are designed and therefore the skill set that's required by engineers entering the industry. And so this is not just limited to the automotive industry, but many others, including industrial automation, manufacturing, energy and utilities, medical devices, aerospace, and of course, education. And what we want to discuss today is digital transformations in education, and more specifically, engineering teaching labs. So, as I mentioned, we're joined by Quanser for this discussion about labs, and Paul will tell you a bit more about why and more about Quanser and how MathWorks and Quanser have been collaborating for a number of years.
I will, and hello everybody, and it would be a pleasure to meet all of you physically, but alas, we're here virtually today, and thank you for taking the time to join us here. Like Will was saying, Quanser and MathWorks, we have been partnered for over 20 years in really bringing to life a lot of these great concepts that the MathWorks and Simulink with model-based design and rapid controls prototyping already bring to the table. And what Quanser does, for those of you who don't know who we are, we take those great platforms and we apply them to our physical labs, be it for both undergraduate teaching and graduate research, and allow them to bring those concepts to life. We have been in this business for over 30 years. You can see right here from our first product on the left all the way to our most recent product on the right. We always embody an academic first approach to everything we bring to the table. And what we do in support of academia is allow students both in the undergraduate programs to experience these concepts on real physical systems, and at the same time, like the car on the right, take those concepts all the way to graduate programs and be able to unleash state-of-the-art research in conjunction with our physical platforms. Very quickly, just to give everyone an idea of the type of solution that Quanser brings to the table along with the MATLAB and Simulink offering. So here you can see a very high level image processing Simulink diagram that essentially takes the video feed of our car, processes that data, and eventually comes up with steering commands to be able to keep the car on a path as it sort of traverses a circle. So this is the beginnings of bringing some of those concepts to life. So this is me in my basement with one of our roadways laid out. In this case, I'm really trying to push the envelope of how fast I can traverse this track, and knowing the only information I have is the lane in front of me. As you can see, after some processing and a bit of tuning, I was able to navigate this fairly at fairly high speeds. If I were to scale the speeds up, this would be in the 70 to 100 kilometers an hour full scale range. So, really a great example of how you can take those theories and, with the power of MATLAB and Simulink, distill them and apply them to a physical system.
Great, thanks so much. And of course, we want to talk about this digital transformation that's been going on in STEM education. And of course, education's been transforming for many years, but COVID-19 has dramatically accelerated this and forced the adoption of new technology in different modes of teaching. And all of you have been handling this firsthand at your universities. And we're focused on labs partially because arguably it's one of the most difficult parts of a course to move online and then administer online. And so I want to take a look at results from a survey that was conducted by Bayview Analytics and was published a few months ago. And the survey was focused on STEM educators teaching online during the pandemic. And there are some very interesting data points, and I want to highlight these, and I have a link to the article here as well, so I encourage you to review it after this presentation. So let's take a look at some of these numbers. About half of STEM professors taught a laboratory course completely online. 40% taught a lab that was combined in person and online, and so we call this a hybrid approach to labs. And then something I thought was really noteworthy was only 2% canceled the lab portion of their course. So this stood out to me, and it underscores the importance of labs to STEM education. And to me, this is a sign that you were really successful supporting your faculty to help get them going online. And then something else that came out of the survey, 72% of STEM professors identified the unique need for online labs in STEM education. So clearly having inadequate methods for teaching a lab online, at least part of the time, diminishes the lab experience for students. So why is this a problem? Well, in engineering education, labs play an important role in student development throughout their degree program or through an individual course. And from a technical perspective, they help students early in their education by reinforcing the concepts they've been learning in class and helping build their intuition and judgment as engineers. Then later, as they advance in the course, they begin to apply their knowledge to maybe some specific design scenarios, and then they can begin to analyze complex engineering systems and really understand the big picture. But beyond the technical aspects, students also develop important professional skills in the lab. They work on teams, complete projects, communicate technical concepts that they're learning, and these aspects fostered by active learning are major contributors to students becoming ready to begin their careers in their respective industries. And this is really our ultimate goal. And to continue with that thread on the idea of industry readiness, I wanted to highlight some of the results from the 2020 survey for skill gaps in recent engineering graduates that was conducted by the ASEE Corporate Member Council. This survey looked at both technical and professional skill gaps. And so here I've picked out 3 technical areas where gaps were identified, and MathWorks and Quanser certainly have contributions to make. These are model-based systems engineering, artificial intelligence, and digital twins. Now, these are skills that are being requested by industries that have been changing the way their engineers are designing and working. And these changes are ultimately being driven by the digital transformations that I mentioned earlier. Now, industry is identifying the need for these additional skills while still having the same needs with other technical and professional skills. Essentially, universities are being asked to do more in the same amount of time or less. While we have all this happening, it's not without significant constraints. So we're sensitive to the constraints on university labs, such as the physical lab space that hardware and students need in those spaces. The scheduling challenges of lab sessions and head caps and getting everyone who needs access to the labs. And then of course the blend of teaching and research needs that may need that same space or attention. So achieving broader technical coverage and continuing to grow professional skills of students while enrollments increase, time space limitations remain in place is challenging, if not impossible, without digital transformation on some level. So one potential solution to help mitigate all of these issues is to use virtual labs to complement existing lab activities, expand the potential learning outcomes, and expose students to new technical areas. as well as extend laboratory contact time for students. So to demonstrate this, I'll hand things back over to Paul, and he'll tell you more about the approach that Quonsor takes and show some examples of combining the real hardware with virtual experiences.
All right, thanks, Will. And this this is a very interesting sort of set of slides that I think are very to the point, especially of what happened during the pandemic. So like I mentioned earlier, Quonsor has been in this business for 30 years, and academia is what we do, is who we are. And when we are here to support you as lecturers, as researchers, drive towards success, whatever that success may be it, give those aha and intuition moments in the lab to your students, or have an open architecture research platform that can really accelerate and fulfill your research goals as well. And really a lot of this is in this, captured in this image, in the sense that because we are academic in nature and we want to make sure that we highlight the rigor of and model-based design of everything that makes engineering what it is, we've always had this duality of how do you take that theory and apply it to the physical and make sure that the physical represents the theory to the best of its ability, and allow for this iterative approach of getting the theory from the lecture. This is exactly what you and your staff as professors and researchers do, day in and day out, and are fantastic at it. And where we come into the pictures, we allow for solutions that we bring into the lab and into the research studio to allow for those concepts, theories to be applied and realized and pushed in the lab. And so this is a virtual cycle that we truly believe in, and we adopted this approach. Traditionally we would have this be very much in person, and you would have ideally a lecture in the morning and be able to come and experience the concepts in the lab in the afternoon. But the pandemic got in our way, and what we're able to pivot to, what I'll show you in the next few slides, is taking the same approach and the same sort of hardware and physical applied approach and bring it to life and deliver it in a virtual context. And I'll show you some examples of exactly how we were able to do that. So at the highest level, and this is inclusive of both our physical offerings and now our new virtual offerings that we've brought to light during the pandemic, this is still our pinnacles. This is what Quonsor stands for, and we will always support this approach regardless of it being a physical and or a virtual experience. We are academically aligned. We ensure that all our hardware is robust and expandable, has that ability to add on to it. And our software architecture, especially when you combine it with the power of MATLAB and Simulink, are truly open architecture and transparent software to allow for any idea that's conveyed in the classroom or theorized in the research to be put to life and to be put into practice. All of our experience are fully documented. There aren't, you're never going to be left alone to sort of figure things out on your own. We're here to support you. We're here to give you all the content that will help you get the job done and be able to realize your success in any various form. And then finally, this is what we also bring to the table, because we are representative of industry and see sort of the best practices that have been evolving, over the last little while, is highlighting these modern techniques of model-based design, rapid controls for prototyping, giving your students and your researchers that skill set to really be able to take their academic profession to the next level. This is a great survey that came out of one of the courses that actually adopted our virtual offering in the fall. This past fall, it was out of York University in Canada. And this is we've had a great relationship. We were not too far from them actually in our headquarters, just north of Toronto, Canada. And over the years and decades, actually, they've been deploying physical Quonsor labs in their undergraduate control systems course. Obviously, the pandemic got in the way, and resoundingly, a lot of our customers were asking us for help. How do they were able to pivot and teach the course remotely. The lab was the challenge. How do you bring that physical, real world experience online? How do you bring it online? How do you deliver it remotely? And so we released a suite of offerings that's called QLabs, Quanser Interactive Labs, that essentially takes some of our most popular undergraduate experiences and virtualizes them. And you'll see some examples of them as well. And what this course actually did was deploy a predominantly virtual experience to their students, and I'll show you what that looks like. But at the same time, they also realized how important it was to make sure that there is a physical reality. So that virtual experience, they had a lot of the physical, products in the lab as well. And so over and above, I believe they did 3 virtual experiences with 1 physical one where a TA would come in and have an audiovisual setup, and the class would beam in, and then the teaching assistant or lab assistant would go through the exercises to really cement the concepts that were being highlighted in the lab. And as you can see from a lot of the feedback, this is all anonymous feedback from the students after the course, resoundingly, they all had a really good experience. And this really allows us to paint a future picture once we're past this pandemic, and we all see the light at the end of the tunnel. And what we're landing on is, it's not a question of should we go virtual and should we go physical. The actual answer is the sum of both parts. Is how do you leverage both? There's nothing going to replace a physical experience in an engineering lab, but how do you augment that? How do you supplement that with a democratized approach to the lab, if you will, by giving everybody a lab on their laptop as well? And I'll show you what we mean by that. So this is a very quick, it's 8 times speed video. What you would see here is the typical demonstration I would do with one of our intro products. This is a DC servo motor example, and basically what this shows is how quickly you can validate the model. So you spend a lot of time in the lecture, deriving that model, and so in the lab you can validate that model, and then based on that model you can very quickly, and this is sort of showing the rapid controls prototyping element, you can very quickly tune a feedback control system that is based on the model that will give you the performance or specifications that you want. So like I mentioned earlier, and here's one of our professors that actually deployed the course at York University. A lot of our customers were coming to us with this question, and I'm sure a lot of you, especially the deans in the audience, having to make these difficult decisions. How do you pivot? How do you deliver everything online? And what do you do with the labs? And so this next video I want to show you is very similar to what I showed previously, but if you realize right now, instead of a physical cube or physical product that would typically be in the lab for the students to access, I have now a virtual product. But the experience itself, and making sure that it represents the dynamics of the system, and it's it mimics the model that was theoretically designed to begin with, are all the same. So the same experience, the same sort of nuances that you would have in the lab, as much as possible, is brought to light in this offering as well. So again, you validate the model that you derived in the lecture, and then by leveraging, what Simulink and MATLAB are great at is this open architecture canvas, and I can bring a lot of these concepts to life. You can wrap different control systems, and you can use that model to actually tune and develop a very specific, feedback control system at the end. And then finally, this is a great video. This really shows, in this case, both of them together. And what you're seeing here is once you do the DC servo motor example, we challenge the students by providing an unstable pendulum on top of it. And the whole point of this exercise is, can you stabilize the pendulum by taking advantage of the model properties? And what we're showing here is how much effort we put in so that our virtual or simulated offering, the one on the bottom there, mimics the physical as close to as possible. And that really takes we sweat the details to make sure that the experience is on par to what they would have had in the physical lab to begin with. Finally, here's another great video that shows one of our more advanced offerings. This is the Quanser ARM that was just released, and funny enough, because we were developing it through the pandemic, this was our first product that we ever actually released virtually first. So you can see the sort of the virtual offering that was released first, and a few months after the fact, we released the physical ARM. And again, the same type of experiences can be had with the physical and the virtual. And we truly believe, again, that the two will really pair well together. And the benefit of something more sophisticated like an ARM is that now you can start putting in various environments that are more challenging. So you can have a conveyor belt, for example, where in the physical lab you might not have the ability to realize a conveyor belt, and you can do other things in the virtual space. So really, moving forward, we are imagining a world where it's both. It's physical experiences, but they are well supported with virtual take home or remote activities as well.
Great. Now, these examples are relatively advanced, and I have to be honest, at first glance with the inverted pendulum, sometimes it's hard for me to tell which one's the virtual and which one's the hardware. But they're really fantastic, and they may fit a little further along a student's progression in a lab course. For example, like this diagram I showed earlier, maybe we're looking at something here. So I'll show another example that will fit a little further down on this chart, where students are using a virtual lab to help build their intuition and fundamental understanding of a topic. So for this example, I want to share a success story from one of our partners, where labs were taught online and in a hybrid in-person and online learning environment. And so this is at the University of Applied Sciences, Dresden. And here instructors in an electrical engineering course needed to provide online access to a signal processing lab. So you can see a photo of the equipment that they're using in this lab here. So to solve this problem, they developed an app that replicated the signal generator and oscilloscope used by students in the lab. And the app was used to allow students that could not access the lab to complete the experiment online. So here you can see what the app looks like, and it has knobs and switches for adjusting parameters and configuring a filter, just like the hardware. The app is not just a simulation, but an interactive place for students to experiment. But it also had another use. It allowed the lab to take on this hybrid persona. So now students that use the physical hardware in the lab could extend their learning experience and continue working with the equipment beyond their allotted lab time. So in this case, the inclusion of that virtual component, it could actually add value to the student lab experience. And using a virtual lab, it doesn't need to be a dramatically different experience. We can stick with the same type of workflow typically used for lab activities. So now I'll show you something that we've been working on at MathWorks, and uses this approach for a virtual lab to reinforce a really fundamental concept. So this example is an air track collisions lab that may be included in an undergraduate introductory physics course for engineering students. And I actually did this experiment myself as a student. So I was really excited when a member of our content team brought forward the idea. But if you aren't familiar with the setup, mass is added to each of these carts, and they glide on this track. And the track's blowing air, which makes a very low friction surface for the carts to slide on. So then students push the carts into each other and observe the results and iterate on this with a few different configurations. So there are 3 stages to the experiment, where using the virtual hardware, students observe elastic and inelastic collisions and how energy is transferred between the carts when they collide. So let's see what this activity looks like now. So here we're using a LiveScript as our lab notebook for recording data and performing calculations. And first, the script walks through some of the background theory of elastic and inelastic collisions before introducing the experiment. Students explore that underlying theory and check to make sure they understand how to apply it before continuing in some pre-lab questions. Then the stages of the experiment are introduced and the setup is explained. And then next, we have the procedure for launching the simulation that's covered. And then the simulation is launched directly from the LiveScript. And the interface in Simulink has buttons for students to press. And what's sort of interesting is how long they hold down the buttons controls how hard the cart is pushed effectively. So it's a difficult thing to replicate. It's a little bit different every time you do it. And here, parameters such as cart masses and their starting locations can be adjusted. So here's the view of that interface that students work with. Again, they get data output on one side, and the other side the buttons they interact with, and they can adjust all the parameters as needed to experiment during this lab activity, or maybe they're doing this after using the hardware in person in the physical lab. And then the results of each simulation are showed in the Mechanics Explorer. And here I have a video of an example output from that. And we also have all the files for this experiment available on our website. So if you're interested in trying it out, please let us know what you think. We're really looking forward to feedback. So some of the key takeaways from what we've been talking about in the examples that we've shown. Hybrid teaching approaches to labs can really expand on that experience of the physical lab for students. And enhancing laboratory experiences long-term by combining the virtual labs with that traditional physical lab approach can be really powerful, often enabling students with a physical system of their own to work with. And students can even access that virtual hardware without needing to come into the lab, so they don't necessarily need security or direct oversight all the time. And this also creates opportunities to enable larger class sizes or even classes over larger geographical distances. And this gives more flexibility to instructors and the students themselves. And before we wrap things up, I want to share some of the resources we make available for users of MATLAB and Simulink that can help them with their labs. So Live Editor is something I showed in that clip at the AirTrack lab. Live Editor creates live scripts, and that's a combination of formatted text, MATLAB code, and visuals. And they can be used to make electronic lab notebooks or lab reports. Students can also use live scripts for their class projects. And that can be what they deliver with their design. And earlier I showed an example from one of our partners, and they created a MATLAB app to represent hardware in their lab. So apps can be created in the MATLAB App Designer. They run in MATLAB or MATLAB Online. There are also apps installed directly with MATLAB. So your faculty might find something that's useful for getting started creating a lab there as well. There are also hardware support packages available for MATLAB and Simulink to help with labs and project-based learning. I didn't mention this in any of our examples, but ThingSpeak is our IoT platform. Students can use ThingSpeak for creating their own sensor projects and then importing and analyzing the data in MATLAB. And we also offer free self-paced training for educators and students. So our on-ramps, which are pictured here, can help students get caught up on using MATLAB and Simulink before they get started in the labs. It's a nice way to get them caught up to speed before they start using the software. We also have a new section of our website to get dedicated to online teaching. And here there's a page specifically for virtual labs and projects. And this page contains a lot of the information on the resources that I've mentioned and that you've seen today. So I encourage you to share these resources contained in this presentation with your faculty and to reach out with feedback on anything that we're working on. So thank you again for taking the time to listen to our presentation, and please reach out if you or your faculty have any questions. We look forward to talking more.